All right, so get to add on to that. So everything that you guys have seen so far in class today is actually just the first half of the story with relativity. It's called special relativity, which is something to do with there are these dilations, including time dilations based on motion. Right? So move through space, time slows down for you. Now, of course, if you are along for the trip with Rocket Twin, for example, you don't notice any of these time dilations inside your ship, but an outsider looking in would notice something, right? And if you met up at the end, it'd be different ages. So that's called twin paradox. What you guys are looking at right here is, now onto this. This is general relativity, which incorporates gravity. If you think about, well, again, this is something Einstein laid out, but this is like over 10 years after he comes up with special relativity, so around 1918, incorporates gravity into this model of relativity. So it turns out that gravity also slows down time. So think about space-time being this four-dimensional fabric, and let's take the 3 dimensions of space and just squash them down into 2 dimensions, like this graph paper looking good right here. Okay? So with this model, if you have a huge mass, say a huge gravitational force, then it will warp that fabric so that if, say, you introduce a planet, it comes along at just moving in a straight line, constant velocity, something like that, then it looks like it's going to orbit around the sun in this case, but not because there's a force like a gravitational tug, but because it's actually traveling in a straight line on a curved path. So this is a reimagining of gravity. So Newtonian gravity, which you guys learned in this class, gravitational pull equals Gmm over r squared. You guys remember that whole thing, inverse square law whole deal? It turns out that it's actually pretty good for like most things that you can use it to predict pretty accurately, like where the planets are going to be in their orbits at particular times for a long time, right? But there are a few places where it breaks down and the model doesn't really stand up and work with it. One of the examples in history was if you look at the orbit of the planet Mercury, it has a weird perturbation that Newtonian physics would not have predicted. So Newtonian physics, you could predict where all the planets should be, and it worked out for Venus, Earth, Mars, Jupiter. It worked out for all those, but Mercury was just has this weird perturbation that can be explained. And for a long time, there's this whole fun history about how people hypothesize, well, maybe there's some alternate Earth on the other side of the sun that follows our orbit on just the opposite side, so we can't see it, or maybe there's a planet that's so close to the sun that we just don't see it because it rises and falls with the sun just during the day. Those ended up not being true. What ended up being was that at the end of the day, Newtonian physics, gravitational force equals Gmm over r squared, is only an approximation of this this reimagining with Einstein physics and this warping of space-time fabric. Now, this general relativity model also explains some other things. For example, gravitational lensing. I think we came across this a few months ago. So if you look, that was also one of the first experiments that verified general relativity. So if you look at the positions of stars in the night sky, they should actually be warped a little bit from this gravitational effect. I mean, what's the largest mass anywhere nearby us? Well, it'd be the sun. That 99% of the mass of the solar system is in the sun. So if you follow the light ray, you guys see just like this green planet, it's going to follow a curved path and would also curve out of place. And so it would appear to be the position of the star in the night sky would appear to be shifted out of place a little bit. Now the catch is you can only really see that if the light ray goes really nearby the sun, and you can only detect that during a total solar eclipse. Now, just by complete happenstance, it turns out that the sun is 400 times the diameter of our moon, but also 400 times further away. And so in the sky, the angular size of the sun and the moon exactly happen to align. And so during a total solar eclipse, which is a pretty rare event, only then can you see the stars in the night sky right around the sun. And I want to say it was like 1919, 1920, somewhere there. There's some photographs taken and they were compared. And yeah, that was actually true. There was a gravitational lensing effect. And so general relativity was for sure confirmed at that point. Of course, there were other evidence that was true, like orbit of Mercury and so on.